I'm Dale Brosius. I'm the Chief Commercialization Officer for IACMI, and this is the November episode of Innovation Insights. So go back to the start. I meant to start here. Welcome everybody. This is a 1-hour session. We'll move pretty quickly through it, and we'll have 3 speakers. So just a little bit about IACMI. I want to go down this. Mainly, we have 3 themes: convene, connect, and catalyze. This is surrounded by a number of activities that we do and bring together. One of the ways we did that is our fall members meeting, which we had a month ago in Detroit. It was very successful. Had great speakers, great interaction, tours of the Scale Up Research Facility, reception at the Henry Ford Museum. This is one of the values of being an IACMI member. So what is Innovation Insights? It's our monthly webinar series featuring products and technologies from our industry members and R&D partners. So a typical month, and this is a good one for that, we have a presentation from one small company, one large company, and one of our research partners. And any IACMI member in good standing is eligible to present. So if you want to get on the agenda for 2022, please reach out to me. The thing is that this is the 6th one for this year. We've all the previous ones have been recorded, and those are available on our website at iacmi.org. So if you go under the events tabs, you get to Innovation Insights, and then you can get down to the previous ones and actually watch the previous versions. They're all 1 hour long, and so if there's something in particular you wanted to go catch, you're able to go do that. So I mentioned December, I'll just go ahead and give a promotion for this. And Kim will post in the chat the link to go ahead and register for next month. But we'll have Lorenzo Mincantele from Helicoid Industries. It's a small company. Bob Yancey from Hexcel Corporation. It's probably a focus on materials for urban air mobility and automotive. And then Derek Berry from the National Renewable Energy Laboratory with some innovative technology around machining and finishing of very large wind turbine blades. So I think that all of those will be very good topics for next month. But we're here, and we're at this month. And so we've got 3 great speakers today: DJ Yang from Graphene, Texas, our TX, Matt Walp from Johns Manville, and Dave Walter from the Composites Recycling Technology Center. So I'm not going to take up any more of their time. I've asked each of them to present for about 15 to 17 minutes, and then we'll have time for Q&A. You can post those Q&A questions in the Q&A tab or in the chat tab, and then we'll get to ask those at each speaker change. So at this point, I'm going to turn it over to DJ Yang, and he'll share his screen.
Good morning or good afternoon. I guess there it's a lunchtime, but my name is DJ Yang, as Dale introduced. I'm a founder as well as a CTO of GrapheneTX Inc. And before I start my talk, I'd like to thank Dale for giving me a time to introduce our company's technology as well as a product related to low-cost carbon fiber, as well as functionalized graphene. Today, I start my talk with a rather very bold questions. EV is our future. Okay, I don't know why.
So you'll just click or use the arrow button to move the next slide.
Yeah, it doesn't move somehow. I don't know why.
So if you want to go out of, so just does it advance on a click? There you go.
Okay, I don't know how I did, but as you know, even though they have a very good in terms of no greenhouse gas production, but they are still building their cars using galvanized steel or metal alloys. So they are, in a way, heavyweight. And also since they are using metal, especially galvanized steel, there are many corrosion issues. And also it requires like multiple layers of a coating. So during the preparing, like for example, window, they did the stamping, and also during the spraying paint, they generate lots of waste. And so it's not really a recycling circular economy yet. So there's a solution. This is a BMW i3 introduced, I think, a few years ago, I think 2019. These are carbon fiber composite cars. And they said it is as strong as steel, and also it's a lightweight. So since it's a 50% weight reduction, you can improve battery mileage twofold since you are reducing the weight by half. And also, since this is a composite cars, you don't have to worry about corrosion, so it has like a long use life. However, still there are problems. It's a high cost, especially due to the high price of a carbon fiber. Epoxy resin is very cheap, but carbon fiber is very expensive. Another problem is using composite, and the appearance is not that good, and also poor depth of image. I believe our product can elevate or solve these problems. So this is the way to solve the high cost carbon fiber problem. As you know, since a pen-based polyacrylonitrile-based carbon fiber introduced late 60s, every carbon fiber manufacturers are in a way using pen-based solution spinning to make a carbon fiber. It involves like a 6-step, and also it requires a high investment based on Oak Ridge National Lab study. Their investment is just $78 million, but if it is a melt spinning, then it will be only $28 million. And also, since you don't go through many steps, and it's a high throughput, especially since you are not using solvent, you can melt spin faster compared to spinning in solution. And of course, it also like a low operation and maintenance cost. So I like to call it, this is really like a green manufacturing. And then here I just want to show ours still it's a pen base, but we have like an additional monomer. So I like to show the melt spinning here. So this is just a laboratory unit. Of course, next stage, we will do like a multiple filament melt spinning, probably at Oak Ridge National Lab. Then you say why it is melt spinnable? Because we know we developed the technology how to create so-called glass transition temperature. Regular like a copolymer pen or like a pen polymer they are using, they don't have like a TG. But as you can see here, it's a reproducible, and we have like a glass transition temperature at 95 degrees C. So we have like a 2 different phase. So that's why we will be able to melt spinning. And then we only use 900 degrees C, and also still the diameter is not as thin as like a 7 micron, but using like a 35 diameter at 900 degrees C carbon carbonization temperature we use, we will be able to meet automotive spec. Okay. And then, of course, if we reduce the fiber and also, fiber diameter, and also if we increase carbonization temperature, we will exceed the performance as I shown here. So as you can see, we can handle the high cost problem, but second problem, the reason why it has a less appealing appearance as well as a poor depth of image, it is due to the moisture. Composite compared to metal, it loves absorb moisture, and also polymer has a UV sunlight damage, and also polymer is not conductive, so they are static. So I will show you we can alleviate some of this problem, or we can solve this problem. We need to develop the lots of data, but I like to show you the preliminary data. As you can see, if you add just 1%, this is aminated graphene epoxy, you will see the increase of hydrophobicity. Okay, then, theoretically, 1 gram of graphene can cover 2,630 square meter. So if you put in the composite, there are multi-layer of graphene, and so they will protect the moisture problem. And then another advantage, as you can see, just using pristine graphene, it doesn't absorb UV light. However, aminated graphene, especially it can absorb high energy side of UV. So it will give you longer stability of a composite by using the aminated graphene. And then there are additional benefits from functionalized graphene. As you can see from left graph, the pristine graphene shows poor or lower tensile strength compared to aminated graphene, and also right-hand side the graph shows as you add more, it will increase a mechanical property. And then the question is why? So if you just use a pristine graphene, it is just a physical mixing. There is no chemical bonding between graphene and epoxy. But if you use aminated graphene, the amine group reacts with a epoxy group, and there is a ring opening, and then it forms carbon and nitrogen bond. So it will give you a strong chemical bonding we call covalent bond. That's why it enhances mechanical properties. Another test we did, this is a so-called compression strength test. We add just 1% of aminated graphene in epoxy. In this case, it's a glass fiber. So as you can see, by adding only 1%, you can increase 10% the strength. That means we will be able to use less amount of fibers when you make a composite. So I already mentioned that by using low-cost carbon fiber precursor, we will be able to lower or solve that high-cost composite problem. Another one is the less appealing appearance problem. By using aminated graphene, we can solve. However, as I shown you the mechanical property data, it will enhance the strength. So it will, using low-cost carbon fiber and aminated graphene composite, you will make it even, you will enhance number 1, number 2, and number 4, items here. So it will be even stronger, and it will be make it even lighter. And also, since it doesn't absorb moisture, you will have a longer use life of composite cars. So our product can be used many applications. So currently we are offer low cost carbon fiber precursor technology. We finished a proof of concept in the lab, and we are formulating next stage by working with IACMI and Oak Ridge National Lab. But anyway, currently we are selling aminated graphene and aminated CNT and alkylated aminated graphene CNT we are selling. So alkylated amine, especially long chain hydrocarbon alkylate amine, it's good for non-polar plastics such as polypropylene or TPO or EPDM. So they can mix well. And also aminated graphene you can use, of course, I already show epoxy resin, but you can use it with like a nylon 6,6 or nylon 6 because that amine group promote hydrogen bonding. So there are many applications. So as you know, especially offshore wind turbine blades, they need to have a longer and lighter. And also I was told that currently the tower is made out of steel, but if they use composite and then it can last more than 50, as the engineer told me it can last 100 years. That means we will have a real saving of maintenance. And also, if we use this material, low-cost carbon fiber composite with graphene use, it can use like infrastructure and constructions. I show you two examples. One is like utility poles and also bridge decks. So they can use longer because these like graphene can be used in other products as well. So what we are going to do, as I told you already, we are selling already like a graphene product. However, as far as a low cost carbon fiber project is concerned, we proved, a laboratory, the next stage, what we are going to do. So we are communicating already with the Oak Ridge and IACMI. So what we will do, we produce enough, like a large quantity of polymer, and then UTD, and we do a little more optimization study of extrusion, and then we'll provide a large quantity of polymer to Oak Ridge National Lab. And then by the time we've successfully finished, I believe we will be able to get investment. Okay, of course, with that carbon fiber produced from Oak Ridge, we can make a composite, and then that composite, carbon fiber composite prepreg can be tried like a TPI and on other automotive company as well. So these are the our company. I think I have just one more minute. So I already mentioned this is a Texas registered company. It's a very young company, but we had a long incubation at UT Dallas, essentially it's 8 years. And then that's about it, but this is my background. So any questions?
Thanks, DJ. Yes, we do have a question that came in, and you talk about the surface appearance problem, the DOI, for example, in carbon fiber. And one of the questions, and I know it comes from a tier 1 supplier, says one of the issues for poor surface appearance of carbon fiber prepreg for Class A is the difference in the coefficient of linear thermal expansion of the resin and the carbon fiber, the difference between the two. So how would the graphene help reduce the difference in the coefficient of linear thermal expansion of the resin and the fiber? So, I mean, will it for example, bring the resin thermal expansion back toward what the fiber is, and therefore you get less of that
Okay.
fiber read through in a composite?
Yeah, that's a very good question, but unfortunately, I don't have a good answer. That I mean, if I excuse, that can be answered by mechanical engineer and physicists. Of course, also, and like once you have a lot of like a thermal expansion data using the sample, so you will take into account, and then you probably make like a mold properly. So, and another thing is, I believe if you have like a better curing, and it may reduce that expansion problem as well. In other words, if it makes a high density, and but using like adding graphene, and I believe at least it will protect the composite part from absorbing moisture, so it will reduce swelling. And then once you have a vicious cycle between like a cold weather and warm weather, then that moisture in the pore, in composite, they may give you adverse effect over stability of a composite. So that's the another thing I can think of as a chemist, and I believe it will be a solvable problem. And
so I guess it's certainly an opportunity here, I think, to measure the difference in thermal expansion of a modified and unmodified prepreg.
yes,
might be something in the future. There's one more. There's a question on the Q&A, and because of time, I'm not going to ask it. I would ask that you go into the Q&A box and,
Okay.
and answer it live for me.
Yep.
While our next speaker is presenting.
Okay.
Okay. Thank you.
Again,
you, DJ.
thank you very much for giving me opportunity to talk today.
Sure. Okay. So if you can stop sharing, I'll introduce our next speaker. So our next speaker is Matthew Walp. Matthew is innovation leader in composites for Johns Manville Corporation in Denver. So, as I mentioned to them earlier, we're working in 4 time zones today. So we continue to move west. We just went from Dallas, and now we're going to Denver, and then we'll finish up in Washington State. So Matt, the floor is all yours.
Thank you, Dale. So good morning, good day, everyone. My name is Matt Walp. I'm the innovation leader at JM for our thermoplastics composites business. JM is kind of at an exciting spot right now. We have been in the process of launching our Neomera Organosheet brand. We did that over pretty much the last couple of months. We've actually been talking about this product and this technology for a fair amount of time, but now we've transitioned over into the commercial side and commercialized it and begun selling these Organosheets into the market. So I'm going to talk a little bit about the origin story around our Organosheet technology. I think it's a nice innovation story, similar like you hear with other innovation stories out there. How did JM come to develop this technology? And what does it allow? What does it enable, particularly when we think about composites and the benefits of composites? So what's an organosheet? Just to get everybody on the same page, organosheets themselves are not new technology. They've been around for a number of years. Developed is really a thermoplastic composite sheet that can be used as an engineered material. So they all have something in common in the sense that they have some sort of fundamental reinforcement. It's typically a fabric. It could be glass fiber, it could be carbon fiber, comes in a roll and is processed. And then the other side of it is the thermoplastic resin, which, often is in a powder or a pellet, a film, and the combination of these two made into an organosheet. These are traditionally produced by melt impregnation. So you have your reinforcements, your fabric, which can be in many cases, different densities, thicknesses, and then your thermoplastic. And when we do this through melt impregnation, you're heating up that thermoplastic resin, sort of the benefits of a thermoplastic, and then forcing it into the fabric, hoping you get really good penetration, ultimately producing that composite organosheet. And these sheets can be used and processed in a number of different ways. Just as a few, you can thermal form them into some sort of standard shapes, and then you can injection over mold them. In this case, the injection over molding process utilizes the organosheet as sort of a structural backbone of that injection molded part. So often injection molded parts can't be used in structural applications. They're either non-structural or semi-structural. This gets you into a more structural material by using all the benefits of injection molding to injection mold in sorts of features. But then that organosheet gives you kind of a backbone to the material to give it the stiffness or strength requirements that you need. So what JM does is not melt impregnation for our organosheets. We produce our organosheets in a fundamentally different process. And the story of how we got there, I think, is interesting to share. I think JM is known within the composites industry for quite some time of producing rovings, glass fiber for composites markets. So we, as a fiber producer, sell those on to other companies that are going to integrate them into their composite, whether those be thermoplastic or thermoset composites. And so for a lot of that time, we've been working on sizing development for our fibers. That sizing development is tailored to certain processes and materials to help utilize and best process that fabric. And we developed a number of years ago a product called Star Rove 886. And this particular sizing development was designed around the use in AP nylon systems. And what we did is develop a sizing that had reactive groups on the surface of the glass to help promote polymerization at the glass surface. And that obviously promotes the polymerization process, but also the bonding and the strength of the interface between the fiber and the matrix. And so what you would get is the nylon would grow off of that surface, and you get a very strong bond. And as you can see in sort of some SEM photos, you end up getting a very strong interface. And so you don't get the sort of the interfacial failure you might see in other materials. So this was mainly designed for the RTM industry. That caprolactam based system, you've got some sort of reinforcement, and then you've got the resin system. Those are mixed inside of a mold, and you get the polymerization inside the mold itself, and then you get your part that comes out of the mold. It's a very interesting process. We still sell this material into that application today, but it does bring some challenges. Number one being our part producer, or in many cases, our customer, is doing the resin chemistry in their process. And that for some can be very doable, and they've developed sort of the capabilities to do that. But many part manufacturers don't have that capability. They don't have that chemistry background, the ability to handle that with their facilities. They're very strong on the part production, but the chemistry side's not so much. And so as JM looked to how this technology would grow and how we could potentially do more with it, we started looking beyond just selling it in the RTM space and maybe doing it on our own. And this is where we introduce our composite technology, our thermoplastic organosheet technology. So, if you're familiar with the RTM process and how AP nylon is produced in that process, first of all, we're running at rather lower temperatures from a thermoplastic standpoint. So right around 90 to 100 degrees C is what we're handling the resin system. And the resin system at that temperature has a very low viscosity. It has basically a water-like viscosity to it, which has a huge benefit when we start to think about application into the reinforcement. And so I use the analogy pretty regularly that if you have a fabric like a jacket or a coat and you pour water on it and it just sort of soaks out the fabric, that's what's really enabled with using such a low viscosity system, that full wet out of the fabric. And then once the resin system is within the fabric, it's polymerized into the nylon. So it's nylon 6. It's a very common, well-known thermoplastic material used in many different places. And for our customers and people who use the product, they're not going to really notice any difference between that and a melt impregnation from a polymer standpoint. Maybe the only benefits would be on the positive side. So by applying that low viscosity system to a fabric, it's then polymerized, and then we produce our Organosheet. And it's a sheet-based product, so that's what we're producing. And it's a continuous process. So we start from fabric, and it becomes a continuous ribbon of product that becomes an Organosheet on the other side. And then right now we chop those into sheets, and that's our product that we sell into the market. So just to give you kind of a view, here's an SEM photo of a cross-section of some material that we've produced. And what you really see is just the full wet out and encapsulation of all the fibers with the polymer. It does a really good job of getting into all those different spaces within the composite. This is really hard to do when you have a higher viscosity system. And that's all essentially virgin AP nylon polymer. So it hasn't gone through any thermal cycling. So it's going to process very well and won't have that history that you would see in a melt impregnation process. So how do you use this? You know, the big one, injection overmolding, I kind of mentioned at the beginning. I think there's a huge opportunity in the markets that are maybe not using as much injection molding as they are today to use it now that's a more structural material. You can essentially functionalize an Organosheet with all sorts of clips, tabs, fins, you know, those types of things, which often when we think about the electrification that's happening in the industry, you're going to have a lot of electronic part integration. And I think Organosheets, injection overmolded will really enable that. And we've seen a number of opportunities there. So in that case, you take your Organosheet, it's heated, goes inside a mold that has this preformed to whatever shape, and then you injection mold around it, and then you pull it out of the mold. And so, you know, injection molding is a very well-known process, I think, out there. So the addition of an Organosheet in that process is not a very difficult next step, and it really then enables that injection molded part to be a structural injection molded part. The other side is what we would consider more generally as Organosheet stamping. I think there's a lot of subcategories of process here: thermoforming, compression molding, and here you're taking a sheet product of some kind, you're heating it up, and it's going in a mold like you would in a traditional stamping, metal stamping process. And you know, again, you just have the preheat step. This is a common process for people today as well, even in the sheet metal side. If you're familiar with hot stamping, this is essentially hot stamping for thermoplastics, but just at a much lower temperature. And then you get the sort of the benefits of a very viscous system when you're trying to form the part. You can create quite unique and intricate shapes. So you know, the story of the Organosheets, I think, is an interesting one for JM. You know, sort of starting as a fiber company, thinking about how we can develop sizings for different customers, and then thinking, okay, maybe we can take on that. We have that chemistry expertise. How can we do that, but still make a intermediate material that then somebody else processes and producing our Organosheet? And so that story, I think, has been interesting for us to evolve in a full range of products. So we obviously are producing these Organosheets in our traditional fabric-based Organosheets like you would see today. So these would be both woven and potentially non-woven fabrics. But our technology enables a whole number of other benefits as well. So we can do quite thick fabrics in one shot. So, you know, in a melt-based system, you may be able to make 0.5 millimeter sheets at one step, and then to get a 3 millimeter product, you have to lay up 6 sheets and reconsolidate those. And every step in that process adds cost. So in our fabric-based Organosheets, like the OS6 series, we're going to be able to be much less expensive than competitors' products because it's a one-step process, both from a 1 millimeter all the way up to 3 millimeter, which we've all demonstrated now. We plan to go even thicker than that. It also can do quite high GSM fabrics, very dense, thick fabrics. The low viscosity of the system really lends itself to that full wet out. We also have our NCF series, which is even more dense fabric. So our process really enables the use of NCF type fabrics. Again, up to 3 millimeters right now. We think we can probably do thicker than that into the future. And the benefit of those NCFs is just the unidirectional sheets laid on top of each other is going to really give you the strength and stiffness that you want for certain types of applications that require that. And then the third series is our CR series, our chopped roving series. And this one's really interesting in the sense that it has all the benefits that the AP nylon system provides, but it also has a reinforcement similar to what you would see in an SMC process, but it's a thermoplastic. So, it's roughly 1 inch long fibers oriented sort of randomly. So you get a quasi isotropic properties from it. And this material really comes into, in a good application when you need a lot of formability. These materials, as you heat them up, and then those fibers are really allowed to move and to flow on top of each other, is going to allow you to produce shapes that you never were able to do with a traditional Organosheet, both because of it being a short fiber, as well as the really good wet out of the reinforcement. So we actually see the CR series as kind of a game changer in getting composites into new applications, because for our customers, both from the processing side, the forming side, as well as the end use side, it's going to look a lot like sheet metal to them, right? If they're familiar and comfortable with forming and designing with sheet metal, the CR6 will sort of enable that similar thing. And so you think of everything a stamping is capable of doing from a formability standpoint, the CR6 allows you to do similar things. And the fundamental ability there is that you've got good strain distribution as you form that product through the thickness of the sheet and through the surface of the sheet. And that's going to enable that sheet metal forming that you see pretty common today, but now all the benefits of a composite material, the light, obviously the weight benefits. And so I think that opens up a full range of applications in the body of a vehicle. For example, if you look at every one of those parts in the car, a lot of those require a lot of formability to achieve. And with a traditional continuous fiber Organosheet, some of those are going to be possible, some are not. But this really opens up kind of a full range of applications when you think about the CR product. And then, really these materials are not limited beyond temperature and those types of things for the application. So we can start to think about mobility as the primary use case for these types of Organosheets. So we have a full range of obviously what's going on the transportation side, with the automotive market being a great opportunity for Organosheet technology. Luggage and containers, again, that movement theme, you're going to be moving it around, you want lightweight. Recreational motorsports, UAVs, and then sporting goods, which has always been an early adopter of composite materials. All the benefits of thermoplastics, and now trying to bring those costs down with an improved process that really gives you a higher quality product with that full wet out at a lower cost. So happy to open it up for any questions.
I've got a couple questions, Matt. One is on the multi-axial. How heavy can you go in those sheets?
Thick?
How thick or what aerial weight can you get to?
For like the CR?
Yeah, the the multi-axial, multi-layer. Yeah.
Okay. Well, so in general, from a thickness standpoint, we've demonstrated between 1 and 3 millimeters today. We believe we can lower probably down to 0.5 millimeter on the thin side, and on the thick side, we really haven't tested the upper limits. The GSM level is very high, like 1200 GSM type fabrics that we're doing.
Sure.
On the series, that can be tailored quite a bit just based on our chopping process. We're actually chopping in line in our process, so we can tailor that to go pretty heavy. But so, we've demonstrated on the fabrics, up to 1200 GSM fabrics, that's on a 1 millimeter thick product. So you just think, 2,400 and then, up from there as you
Sure.
go to different risks.
Okay. So what's what's the typical resin content or fiber volume, however you want to represent that for these materials?
We target 68% on the high side. So obviously we can do less than that, but that's what we've been demonstrating on the line today.
68%
By volume.
fiber by weight. So 32% resin by weight?
Yes, by weight, yeah.
Okay. All right. Yeah, we have one last question is, do you have any numbers for the strength and modulus, tensile strength and tensile modulus for these various materials? I mean, is that available on your website or is it?
So if you reach out to us, we can provide you technical data sheets that has the characterization. It's going to depend obviously on the reinforcement quite a bit. So, specifically a 2-2 twill, what thickness, so we have that information available.
Okay, will you go into the Q&A panel and answer that for me?
Absolutely.
Okay, appreciate it. All right, we need to move on, but thanks, Matthew. Great.
Thank you.
I've been waiting a long time for you guys to roll this product line out. I've been seeing the
Yes, us as well.
over
It's been fun. We finally got there. Yeah.
So yeah, I'm glad we were able to finally get it out there. So, all right, appreciate it. Thank you very much. Okay, so our third speaker for today is, and we're going to switch gears a little bit and go into circular economy recycling, is Dave Walter. Dave's the CEO of the Composites Recycling Technology Center in Port Angeles, Washington, and been following them for a long time. And they've done some really cool things with scrap prepreg that I think you'll be impressed with if you have not seen them before. So Dave, show's all yours.
All right, thank you so much, Dale. Can you see my screen okay?
Yes, sir.
All right, excellent. Well, thank you, Dale, the IACMI team, for the privilege of being able to be here with you this morning. And DJ and Matt, thank you so much for your excellent presentations. It's my privilege to be able to share a little bit here with you. What I'd like to do is just give a really brief bio on me, and then we'll talk a little bit about the CRTC. I'd like to get into some of our innovations and couple of the development projects that we're working on right now. And then I want to share some key learnings. Not an expert by any stretch, but we have some, I think, some hard-earned lessons that maybe I can share with you that might be helpful, and hopefully we'll have time for a few questions here on the back end. So I had the privilege of being able to work for the DuPont company for right out of college, 24 different positions in 8 locations. So I got to see the world with the corporation. It was a wonderful experience, outstanding people. But I was in engineering, sales, marketing, and then ended up in senior leadership. Did a lot of project management in the corporation. And one of the cool things that we had the opportunity to do was to help the DuPont Building Innovations business go from 81 million pounds of landfill in 2008 to 0 by 2011. So they became the first business in the corporation to be landfill free. And that really helped to drive some of my love for sustainability. Really got me plugged in on that side. And so when I retired from the DuPont company, I got to be CEO of the CRTC. So let's talk about CRTC. We're a 501c3 not-for-profit. We've been in business about 6 years now, and we design, develop, and make products that utilize carbon fiber scrap. Okay, and in doing so, we eliminate landfill and help to create jobs. So we're really about sustainability and economic development. When I give talks like this, I like to talk a little bit about megatrends, and you all are aware of this, but I think it's just a good thing for us to keep kind of front and center. There's about 7 billion people in the world today. The UN estimates by 2100, there's going to be 11 billion. About 1 billion of that growth is going to come from Asia. The rest of the world stays relatively flat with the exception of Africa, which grows from 1 billion people to 4 billion people. It's really amazing. Lagos, Nigeria is expected to be the biggest city in the world by 2100. It's hard to imagine. But that's going to be a big stress on the earth. And you think about how will 4 billion more people get fed? How will they get clothed? How will they get housed? I think it's cool that our industry, relative to carbon fiber, has the ability to have some influence on some of these things. And I think if there's ways that we can help keep stuff out of landfill, create jobs, at the same time try to work on some of the big problems of the world, I think that's pretty exciting and a neat triple bottom. So let's talk about the kind of the product here, what we do. So we're dealing just with prepreg. We're not doing any crackback of cured product. We're not doing solvolysis or pyrolysis. We're strictly dealing with prepreg. So we take virgin prepreg rolls that can't be used for their intended purpose, but still have usable life. And so companies can donate those to us because we're a not-for-profit. They get a tax donation for that. And then we can take that and turn it into other material or turn it into other products using that material. So we can use a wide variety of fibers and resins. Normally this stuff is going to be out of the aerospace, sporting goods, transportation, and wind industry, but it's virgin material, failed spec for some reason. And so we intercept it and we're able to repurpose it. So we're really about innovation, right? So we're innovators. We come up with ideas of how to use this material and turn it into a product that we can then sell. And in getting revenue from those products that we sell, that helps to fuel our growth and keep us alive. So we've scaled 18 products from inception to commercialization, and we make all of those products here in our facility in Port Angeles, as Dale mentioned. We've got 5 presses, full machine shop with the CNC to do all our metal work. We've got a big 5-axis CNC that you can see a picture of down below. Water jet, tube rolling, sheeting, slitting, chopping. Pretty good sized facility, about 25,000 square feet. And we're at about 20 team members, so designers, engineers, and technicians. And you can see some of the pics of some of the equipment that we have here at the facility. So we have the full ability to design it, but then also manufacture it as well. And some of the products that we make, just starting in the upper left-hand corner, that's a portable pickleball net. And then there's a park bench. And then you see a sporting bench or an athletic bench. We also make a brace, an orthotic brace that goes on a cuff and a foot plate to help people be able to walk again that have lost functionality in their legs. In the bottom left there, you see a hydrofoil for a surfboard. It's a pretty cool product. And then reel-to-reel tape take-up reels. Who would have thought? But it's actually a pretty interesting space. We make a camper panel for a high-end camper. We do a lot with chopped, where we can take carbon fiber, chop it, press it, make panels for aesthetics, things like knife handle blades, that kind of thing. And then we also make full 4x8 sheets of material that would be used for decorative aesthetics typically, but that would be a carbon fiber panel that might have a wood veneer on the outside, or it might be coated in some way, or could have powdered metal on it. There's a lot of things that we can do with that, but it's usually in the aesthetic space for commercial environments. One of the development projects that we're working on is our advanced cross-laminated timber. We call it the ACLT, but this is where we would take a thermally modified wood. We would put it into a CLT, but we would integrate carbon fiber into that CLT. So you can see in the picture there, you see those little black squares. Those are rods really of carbon fiber that are going the entire length of that CLT panel. So kind of think of it like an integrated I-beam that's built into the wood. It allows us to have a quick erect wall panel. So a 240 square foot home can go up in about 3 days. So backyard ADUs or tiny homes, homeless housing, disaster housing, military housing, things where you need to get shelter up very quickly, but be very durable. And so that's what we've been working on with the ACLT. And one of the cool projects that we've got in motion right now is with another not-for-profit by the name of Pennies for Quarters. And we're working with them to build 24 homes using our ACLT system that's going to provide housing for homeless veterans. And you can see a picture of what it's going to look like there on the right-hand side. But this will all be made with our ACLT panels. So we're really excited about this. It's going to be a cool project and a neat way to give a hand up. One of the other developments that we're working on is a marine cable. So as you know, plastic is often used today for fishing and vertical farming, but that can degrade and shed plastic over time because of the UV exposure. And it could also entangle marine life if it breaks free. And so we've been looking at a different solution to actually utilize carbon fiber in that space. And the nice thing there is that it won't shed and it won't entangle. The stiffness is such that it can't wrap around any marine life. So we're right in the midst of actually testing this. And this is a project that we're working on with Dow AXA. I really appreciate all of their help and leadership, but we're taking spar cap material from them that would normally be in a windmill blade. And we're able to take that, cut it down into very thin pieces or lengths, and can actually then use that as the grow line to be able to do vertical farming. So for example, in a vertical farm, you'll have at the very top of the water, you might suspend macroalgae, seaweed, for example, kelp. And then underneath that, you would suspend a cage that could have mussels in it. And then on the floor of the water, you would have another cage that could have oysters. So it's all suspended in a column of water. And it really helps having something that's very strong and very stiff. And carbon fiber works great in that space. So again, we just went into the water at a shellfish farm not too far away from Seattle. And so we're excited about that and anxious to get it into additional applications as we go forward. So we started with this slide on the mega trend. Hopefully you've seen that we're kind of looking at some different ways to help feed people, maybe with the marine cable and vertical farming applications, house people with the quick erect ACLT wall panels, help people be able to recreate with our pickleball net and our benches and the like, help people from a medical perspective, where orthotic braces and pop-up medical clinics that can be used with our ACLT panels, and of course, doing what many of you do, which is helping to lightweight things to help reduce CO2. And doing that all while we keep carbon fiber out of landfill. So with that, let me summarize up and then get into some key learnings. So we've been in business for about 6 years. We've grown from 1 team member when we first started to 20 now. We've scaled 18 products from inception to commercialization, and we consistently score pretty well with our team member engagement, which is really important to us. So from a premise standpoint on innovation, we really frame it to say that there's no such thing as failure. You really have to reframe your concept, we think, around risk, because it's really all about learning. I remember at DuPont, I used to get asked a lot from a project leadership standpoint, how are you going to de-risk this? And the challenge here is that by definition, when you're innovating, you're making something new. And that means you're going to try some things and they're not going to turn out the way that you hoped. So it's really not about eliminate the risk. It's as much to me about building a team that's able to overcome the setbacks. And we like to say lean forward or learn forward fast. And the reason for that is you're going to make, assumptions that are going to prove to not be accurate. And how fast are you going to get to those assumptions and get the feedback that's going to allow you to make the changes that you need to as you go forward. And one of the things that we found to be really helpful is we get a customer for the product right up front. So as part of our innovation team, they're with us. And the nice thing on that is you learn a ton from them on the things that they need, but you've also got a built-in buyer on the back end, as opposed to waiting to get that customer pulled in until you've got a prototype. We like to have the customer in on the design. And so make a lot of prototypes and iterates. As my friend Dave Banks says, if a picture's worth 1,000 words, a prototype's worth 1,000 pictures. And I 100% align on that. I think it makes a lot of sense. And customers can get a much better sense of it as they get a prototype to be able to work with and touch and feel. But we like to get lots of customer feedback. We find that it's really helpful. We get it across geographies and segments. What we really learned is what we think about it doesn't really matter. It's what the customer thinks about it in the end, but not all customer feedback is equal. And the skill is really knowing the difference there. We also find that the customers who pay give much better feedback. So we don't give any prototypes away. People have to pay for them, but then you really find that the feedback becomes quite genuine. And you relentlessly learn from what the customers are telling you. So closing, innovation is hard. You guys all know that. It's really challenging. But to me, it really starts with hiring. I think we had an advantage of being a startup where we've been able to scale with innovation in mind and look for the people that we felt were going to be able to help us in that space. I've also seen that innovation can be killed by bad culture. And as a leader, you get the kind of culture that you allow. And so, I spend a lot of time as CEO on culture. I just really believe that that's a sustainable advantage if you get it right. but it takes a lot of time. It's not easy. I mean, we could get into a whole nother talk on that one and get a lot deeper into innovation and culture. But one of the things that we like to do is actually celebrate when things don't go as expected. You know, it's easy to celebrate when you win, but when something fails, it doesn't look the way that it's supposed to. It wasn't what you expected. We celebrate that. We'll have sessions where we get everybody together and we talk about it. You know, what did we learn? How did we iterate? What did we do? Did we pivot? What happened with the team? How did the team display grit to overcome? Because in the end, you want to make it a safe place to explore. And sometimes things aren't going to work the way that they're supposed to. And what did you learn from it? That's really the key. So there's my contact information. If I can ever be of help, please always feel free to reach out to me. And with that, if we have a minute or two left, Dale, I'm happy to answer any questions.
Dave, great talk. Can you just mention your relationship with the community college there and how they work with you and what you're doing to help with workforce development?
Yeah, thank you, Dale. That's a great question. So yes, Peninsula College, which is a local community college here in the Port Angeles area, they are very innovative in terms of trying to do workforce development. And we have a partnership with them to be able to help train students. We've hired several that have gone through their program for composites and advanced manufacturing. And so we can do internships with those students where they're able to work while they learn, and then ultimately also be able to be hired by us. So it's kind of cool because we get a chance to see those students in our facility and really get an understanding of whether they're going to be a fit for us, and then can offer positions to them when they're finished, but also can provide mentorship. And we give them an opportunity to be able to work in our facility and be able to have access to state-of-the-art equipment and that sort of thing. So it's a great win-win and really a cool opportunity.
So if they've got somebody's got an idea for a project, they can come in and obviously help develop it hand in hand.
Yeah, exactly.
Yeah.
Yeah, it's a great way to do it.
Okay. Your comment about, I guess is Dave Banks' comment about, about if pictures worth 1,000 words and a prototype's worth 1,000
I like the
pictures.
quote.
Couldn't be more true, especially, now that we're back to kind of in-person trade shows and stuff like that.
Yes, sir.
It's very difficult to convey through, well, even the kind of medium we're in on right now, as well as just photos about the value of composite materials and what they can do. So
Exactly.
being able to touch and see and feel things is so much more important.
Yeah, and you get such great ideas where somebody says, well, that isn't exactly, but what if it, and as soon as you hear that, that can be gold, because it can open up doors for things that you had never even considered that the product might be a fit for.
Yeah. I thought the pool bench thing was, I think that's in locker room stuff.
Yeah.
That's some really cool stuff. And I'm hoping that you guys are starting to get some traction, outside of the local,
we are.
area
Yeah.
there. You obviously have a test facility there with the local pool facility, but yeah.
Yeah. Well, actually, we just finished up a pretty good sized job at the Climate Pledge Arena, which is the big renovation that happened in downtown Seattle, where the NHL Seattle Kraken are playing, and so they put in a bunch of those benches. So that's pretty cool because it is neat, sustainability story with the Climate Pledge Arena. So yeah, that was a neat job for us.
Yeah, it really is. Okay. Great presentation. I mean, I just always have been impressed with, the kind of clever things you guys have come up with and continue to do so. And I hope that people will come to you with ideas as we go forward. So,
well, thank you. Thank you so much. And thanks for all the great support from IACMI. We wouldn't be here without you guys. So thank you.
Thank you, Dave. Okay. So we're right at the 1 hour mark, and that concludes today's Innovation Insights webinar. I want to thank everybody for attending. Don't forget to register for the December 13th. There's a link in the chat there. If you click on that before we close the session, it'll take you right to where you can register for it. So hang on just a sec. Yeah, we just got somebody else is saying thanks to everybody. So we are good for today. Again, thanks to DJ, thanks to Matt, thanks to Dave, and thanks to everybody that's attended. And hope everybody has a great Thanksgiving holiday, and we'll see everybody in December.
Thanks, Dale. Bye, everybody.
All right. Bye-bye.